All right, so we're going to review Mission 6, Basics of Sampling Distribution, with the introduction, and we're going to focus a little bit on the percentiles, I suppose, given what you said, Walter. So if you look at, see what page this is page 94. So this is where we revisit the z-scores. This might not have been in the modules per se. That might have been the issue. But the way I think about z-scores is essentially a standardized measure of distance from the center of the normal distribution. So because of the assumptions we make about the normal distribution as a probability distribution, we can see how far to the right, to the left a value is, and use that threshold to estimate percentile. So we're using ACT scores or SAT scores, which in the United States, if you're from the Midwest, you might use the ACT score. You don't even know what that means. Academic competence test, perhaps. I hear a little bit of background noise. If you could, I think Walter, would you mind, or someone else perhaps? I want to make sure we have muted you guys. Okay, thank you guys. All right, cool. So z-scores are a big issue. It's really the reason we use z-scores is kind of as a placeholder. It's just, in essence, a distance measure. And if we go to the assignments, we should look at, I think we'll find that. But let's just, I'll walk you through these three components, and it's already 8:17. I'll try to get this in about a half hour. Now, I mentioned that we're a demographer. Now, I was just talking with a colleague of mine. He called a demographer a bean counter. And I think we often view demographers as people who simply just are obsessed with numbers. It's maybe overly obsessed with numbers. And I think actually demography, as I said last time in preparation for the week, going over the code and some of the concepts, that demography is probably the earliest kind of statistics because it dealt with life and death situations. And the point that we're trying to make here is essential to the rest of the course, which is this idea of inference. The verb we're using is to infer something. To infer means to take a specific instance of something and make a general statement. So you could infer from a person whether or not that person has other attributes that you do not observe. In statistics, right, Sherlock Holmes, you could say, would infer something. He might observe, say, something about a person, and then would infer from that person's attributes. Maybe they had a broken nail, and he would infer that they were at the crime scene. Well, we have a much more systematic way of inference in statistics that has to do with taking a random sample, which is a small collection of observations, and we use assumptions about the normal distribution because we have a random sample to say something, to infer a general statement about a population. And the population is what the sample represents. And with the code, we actually showed how you can actually take samples of a population. In other words, the census of the Iowa census, right? The state of Iowa in 1915 had a census. It had collected all the people in Iowa and collected information on their income and education, and that's the census. A census, by definition, is everyone, and that's the population. So whenever you have a sample, you're going to want to ask yourself, when you're doing a statistical analysis, what are we inferring to? Is there a population that we're inferring to? And sometimes we aren't inferring to a population, but most of the time in statistics, we are. And this is the profound, sort of the, I would say this is the core of statistics. This is the hardcore assumption of statistics, that we can take assumptions about probability from a random sample to make an inference about a larger population within a degree of confidence. So in this case, we're not saying we exactly know what the population is. We just can infer what the population is within a degree of certainty or uncertainty. So the first few questions have to do with, the question 1 is pretty simple here. It's 0.5 points. It asks, as a demographer, you are trying to understand how you can use a random sample of data to say something about a population. That is, make inferences about a population. You begin by analyzing the data from the Iowa census conducted in 1915. Since this was collected from a census, it consists of the entire population. So in R, you might see, I'm sorry about that. In R, you might see output such as that. I'm going to close paste. I'm sorry, that's what happens. You might see output such as this, which basically, because it is the census, we have descriptive statistics that we describe not as what we call an X bar, right? So an X bar would be written as this, right? If you wanted to write a sample mean, you have an X with that horizontal bar here, and that would be simply you would add up every observation for age, every person's age, and then you divide by the number of observations. You do the same thing when you want to find the average for this population if you have the census. The big difference here is you have mu, this little thing, and kind of draw like a little longer M, kind of curve it, and a little bit, make it a little shorter. That's called mu. It's a Greek symbol, if you know Greek, or even if you know a little bit of Cyrillic or even Russian, you might even see this. And that's simply the mean here. So keep in mind, mu is the mean for the population. That's really all we really want to emphasize here, and that's convention. You're not going to really see many exceptions to that. Okay. Question 2, using the same output, what is the population standard deviation, sigma, for age? Keep in mind now, instead of using, say, a shorthand for standard deviation like SD, we're using another Greek symbol, sigma. Right, so this is how you write it out, sigma. And of course, this was popular if you follow astronomy. There was some major finding in astronomy about the probability of a particle existing being 6 sigma away from the mean. That's actually technically a z-score. It's kind of saying the probability of I'm going to show this Wikipedia page to you just to kind of give you an idea. Well, actually, it's 6 sigma is something else, but you might hear the word sigma in other fields such as astronomy. You'll say the probability of something existing is 6 sigma away from the mean, which means that in a probability distribution, it's a description of the distance. But in this case, in applied statistics, in the social sciences, sigma merely refers to the population standard deviation. All right, so keep in mind Greek population, and that it's unobserved technically unless you have the census. And in this case, we are privileged to have the census. But like everything in life, things cost money, so you probably are often going to be tasked to do an analysis that will not have a full population. And this is what we do in question 3. Now suppose you don't have the entire population and you took a random sample without replacements of 5 people from this population and calculate the average age of the sample. Technically, it doesn't matter if you take one random sample of a population, whether it's with or without replacements. The point is, you just grab 5 people from the ball, basically from the bin. So imagine you have a bowl of marbles. Let's see if I have something similar. Imagine you have a bowl of marbles. You take 5 of those marbles out, and then you average those. And the idea is that those are randomly sampled. This is where probability comes in. Now take a look at the nomenclature here. Nomenclature, fancy word for term. We have X bar. We call this X bar. This is the sample mean. Take a look at it. What does the sample mean here? Well, it's 39.6. 0. Now you can add a 0 there because in R, if there's a 0, it's basically the same. But take a look at this. When you take a random sample of just 5, you can get a mean that is an estimate that is pretty far off from the population mean mu. Population mean mu is 28.5. The sample mean, when you just randomly sample 5, could be 39.6. Now, as we showed before, you could take another random draw from the sample and find a different mean. The point is, the smaller your sample, the more likely you are to be have uncertainty, less precision, less certainty that you're going to be close to the mean. That being said, 39 isn't extraordinarily far. It's not 1,000. It's not larger than the maximum value, right? We have the maximum value of 31 here, but the maximum value in the sample is 100. So you won't have you won't have a value larger than 100 if you take a sample, for instance. But you won't even know that, right? Keep in mind, you won't know that typically. You won't know the population parameters. So the way I remember this is, if you have ever seen Julius Caesar, Shakespeare, there's a famous phrase. And he said, where one of the actors says, "It's Greek to me," simply meaning, I don't know what this means. That's because in the Roman Empire, they spoke Latin and they spoke Greek. A lot of Romans who spoke Latin did not know Greek. Well, keep in mind, just remember, whenever we're using Greek to describe a population, and those are values that we probably don't know unless we're doing a census. And most of the time in statistics, we're not doing a census. The sample standard deviation S is 22.3. Again, that's just the standard deviation of the sample. Okay, question 5. This is where we fill in the blank. We just have to select one of these options. Again, this is my strategy. We have 1 point here. I first think about the statement and what I would say, put it in my own words, and then I'd look at the options. So, because of blank, the mean of one random sample from a population is likely to differ from the mean of another random sample from the same population. And the correct answer is sampling variability. That's the term we want to talk about. And that's what I was showing you before last week, but also even here, essentially showing that when you take 5 participants out of a census, you see that it varies from the population. Well, if we compared one random sample of 5 with another random sample of 5, you're going to see sampling variability. Okay. The other concepts just simply don't make sense. I hope this should be clear. I mean, it has nothing to do with any of these other issues. The median, nothing. We're talking about sampling variability. Okay. Now we have 2 fill in the blanks. The mean of a population is a blank, while the mean of a sample is a blank. We want to distinguish between population parameters and sample statistic. We had it reversed as the other option. No, that's not the case. A population parameter is different than a sample statistic. The word parameter here is somewhat interesting because parameter is sometimes used in math to kind of defines the conditions that are possible, right? In statistics, I'm going to read you the definition of parameter: a numerical characteristic of a population as distinct from a statistic of a sample. More generally, it's a numerical or other measurable factor forming one of a set that defines a system. So it's really, think of that, the parameter, as something that's fixed because it's something that's out there that's real. The sample statistic is not parameterized. Okay. Now we're going to ask a question. Hypothetically, suppose you took many, many samples of 10 people from the population. each time calculating or estimating a different sample mean for age. So we're going to take x bar, x bar, x bar, x bar, x bar, and then we're going to average those means. What are we going to get for that? And here, we're going to get something that approximates, if we scroll up, we're going to get something that approximates the population parameter mean. And that's because when you average, hold on for a second. Yep, there we are, question 8. That's because the point of this question is to make the point that when you know the population mean and population standard deviation, you know, wait. Did I say that? Oh yeah, okay. Yeah, sorry. For question 7, the average of means when the sample size is 10 is going to converge, is going to be right on the population mean. It's going to be on mu. Now we have a sampling distribution of means, and we point out correctly that it can be approximated by the normal distribution model. So that means we're taking basically random samples, averaging those, and then we're taking the averages of the averages. And the averages of the averages create that beautiful bell curve. And that bell curve becomes more precise, the tails become thinner, the peak becomes taller, the larger the sample size becomes. So for question 7, or for question 8 rather, we prompt you to look at the output. The sampling, and we describe the output. The sampling distribution of sample means can be approximated by the normal distribution model. Again, as a reminder, this is not normal in any kind of normative or ethical sense. It simply means it's just a conventional term to describe the bell curve, the type of shape. And here we have the variable for age from the 1915 Iowa Census. And we're going to answer the next 8 questions here. We're going to run those calculations. Now, we're going to ask you, based on what you know about the population mean and population standard deviation, what is the mean of the sampling distribution based on the sample size of 50? Well, given what we know, the mean of the sampling distribution is going to be the population parameter. And then we point out, based on what you know about the population mean and population standard deviation, what is the standard deviation for the sampling distribution based on a sample size of 50? Now here is where we estimate variability based on the sample size. Because remember, our precision of the population estimate increases. That is, the variation of the range of possible estimates, our cone of uncertainty, decreases the larger n increases. N is our sample size. It's a lowercase n, often italicized. So when we take and we estimate the standard deviation here of the sampling distribution by taking sigma, our population standard deviation, dividing it by the square root of our sample size. And that'll be 2.77. Now, if we took a square root of an even larger number, say the square root of I don't know, of 1,000, then we'll take a small number divided by a much larger number, it'll be even smaller. If n were, so the point that to understand here is that while sigma, if we know the population parameters like the standard deviation and the standard deviation, the mean, which is mu, then we can just include those. However, our precision based on the sampling distribution depends on the sample size, and that's what we're going to put in for n. That's all you have to do. And the pedagogical point is, in reality, quite often, we're not going to have the sigma, we're not going to have the mu, we're not going to have the population parameters. But what we're trying to show is that we can estimate based on the sample with reasonable certainty the range of plausible values of the population. And that range of plausible values shrinks. That is, we are become more precise the larger our sample size is. For question 10, we ask, using what you know about the population mean and population standard deviation for age, what is the mean based on the sampling distribution based on a sample size of 100? Well, guess what? Our mean is going to be the same based on the sample size. The mean of the sampling distribution is going to have a point estimate. It's going to have it's always going to converge on the population mean mu, which will be 28.49. So this is like sort of a gimme point. We could have that number be 1,000. It'll be the same. What's going to happen though is we're going to divide our sigma, which is the same as before, right? Because we see the sigma up here. I'm going to scroll up. The sigma is this standard deviation. So we just take this and we divide it by the square root of 100. So just keep in mind your order of operations. You want to square. You want to estimate the square root of 100 first. And you take that about 20 divided by 10. It's about 2. Now that's an interesting value because it's about 2 sigma away. Well, I don't know. Well, we'll talk about it later. It's about two away from 2 years away from the mean. So if we think about the interpretation, you could say, okay, we would estimate on a sample size of 100, that's going to converge on 28.5, the average age, plus or minus, on average, it's going to vary by about a year. Now, we doubled the sample size, but we only decreased the standard deviation of the sampling distribution by 0.77, right? So we went from about 3 to 2, even though we doubled the sample size. So the point is we have depreciating gains that are greater the sample size. Now, we ask you to write an answer in. Maybe this is what one of you had mentioned, James. Using what you know about the population mean and standard deviation for age, what is the mean of the sampling distribution based on a sample size of 100? I already told you this. It's going to be the same number. You shouldn't have to write that margin in part here. That's just the answer that we give you. This would be as if there was rounding error. So if you maybe wrote 28.49, let's see, 494, and you got the wrong answer. We'll fix that, but I'll double check that. But that you should typically ignore that. That's just for our computer's sake, because rounding errors are not that important in general, because we're talking about an estimate. We're talking about a range of plausible values. Okay. Using what you know about the population mean and population standard deviation for age, what is the standard deviation of the sampling distribution based on a sample size of 1,000? What are we going to do? Well, we're going to take our sigma. We're going to divide it by the square root of 1,000. All right, so let's just do that. Look at that. Now look at this. This is actually quite low. On the other hand, if we compare the standard deviation with a sample of 1,000 versus 100, yeah, we shrink our standard deviation. So our precision increases from plus or minus 2 years to plus or minus 0.6 years. But we had to increase our sample 10-fold. In other words, it would cost 10 times as much money, assuming it costs the same amount to sample each individual, to decrease our precision by about 1.5 years. So typically what we do in statistics is we have sort of an a priori or sort of before analysis criterion that we kind of agree on that, okay, we can accept this margin of error, or this is how much money we can afford. And most of the time we can't really afford to do a very large sample, but we do the best we can. and very rarely would we do a census. So question 14 asks, does the center of the sampling distribution change as the sample size increases? Okay, we've asked this question about 4 times. The answer is, of course, no, it doesn't. And that's the reason we're being redundant here, is to drill home this concept, and it's never going to leave you. It's going to be at the center of statistics. And this is the point of the central limit theorem, that the center of the sampling distribution, the average of random samples of a population, stays the same as the sample size increases. The center stays the same. What happens to the spread? Well, as the sample size increases, the spread of the samples distributions decreases, right? So this is sort of, I think I have an example here. Let me see if I can get this here. Yep, here's an image. I'm gonna see if I can. I'm just going to show you an image, just I think because some of you might, find this to be a little more useful. Hold on. Okay, it should be on this. That should be on the home page. There we are. Good. Here, just dragged and dropped an image. Okay. So this simply shows. Don't pay attention to the squared terms here. Think of this as just sigma. The point is, here we have a population average of 0, 0, 0. For the blue, we have a population average of 0. You can even ignore this. This might even be a little confusing. But I want you to pay attention to the fact that for the sampling distribution, the mean will stay the same, and it'll look like this. You have a high peak here, and the center of the distribution will remain the same. But as you increase the variance in this case, because it's the square, you're actually squaring standard deviation, right? Sigma squared is variance. As you increase sigma, we'll just say sigma, you can even ignore the little square terms. You have 0.2, you have a very small one. The peak is high, and the tails are very thin, right? So as this sigma is smaller, the center increases. There's a push and a pull. So spread decreases, the peak increases of the normal distribution. Here we have a sigma of 1. Here you have the peak be a little bit lower. Right? It still looks more probably like a classic bell curve. Now we have a sigma of 5, and we have the same population mean. The center is the same, and this looks like a little slope. It looks like a hill. We'd still call this a bell curve because it's symmetric. It's roughly mound-shaped. So the point is, the blue, the red, and the green all have the same area under the curve. All that differs is that when we increase sigma, or the sample, the standard deviation of the distribution, we are decreasing the height of this peak, or the center of the distribution. Now, of course, to confuse things for a little bit, just to show you that we can, basically put the mu anywhere. In this example, they have the center of the bell curve at -2. That doesn't really mean anything in this case, and it's not relevant to understanding sampling variability and the central limit theorem. But it does give you an idea that basically the origin or the center of the sampling distribution we often will define as 0 normatively, or it'll be the population parameter if we have the population parameter mu. It'll be that value. But the point is, the shape, all we do is when we have the population parameter, mu, all you're doing is changing the position. You're not changing the shape. what changes the shape is the sigma. Okay, I hope that made some sense. I think it's better to visualize that because we don't really show that too much. Okay, so that's what I basically showed, right? As the sample size increases, the spread of the samplation, as the spread decreases. That was the blue, bell curve, the one with a very high peak. Okay. So question 16, also worth 1 point. As the sample size increases, would you expect the sample mean to lie closer or farther from the population mean to the sampling distribution? Well, we'd expect to be closer because the sample size increases, the standard error of the, because as a sample size increases, the standard error of the sample mean decreases. In other words, to take the example of the standard, the sigma as a measure of the standard error, as an estimate of sampling variability, you're basically showing that the bell curve decreases. And I'm going to show, actually use the slide so we can have a common reference. Standard error. So this is the standard error of the sample mean. This is just the, on average, how much does the population estimate, how far off is our guess is the best way to put it. And we can show, here we have, for question 16, we ask, as the sample size increases, would you expect the sample mean to lie closer or farther from the population mean? Well, here we have an example here. On slide 50 of this week, we compare an n of 10 versus an n of 100. We often refer to samples as n with an italicized lowercase n. So you'll often ask, and if you're talking among statisticians or social scientists, we're saying, what's your n? That's the first question we'll often ask. And we mean a lowercase n when we talk about the sample. Well, if you look at this, as we increase the n, we have our decrease in variability, right? This almost looks like the Burj Khalifa. It's like a really tall tower. You have the center at 30. It ranges from what, 36 to maybe 22. This ranges from 50 to 10. This is much less precise. You're still gonna have an estimate, but it's gonna be just less precise. To use the metaphor of signal and noise, there's going to be more signal with the larger n of 100, and there's still going to be some noise, and there'll still be a signal with a sample size of 10, but there's going to be more noise. So there'll be more noise to signal. Okay, that's question 16. Okay, question 17. How many observational units are in the population? The correct answer is simply this here. That's pretty easy, I hope. How many variables are there in the data set? This is just another sort of exploratory question. So I gotta get to the mouse again. That should be relatively easy to answer. And this is from the code. What is the average years of education in the population? Rounded to decimal places. So some of this is from the code. I think. I want to make sure that did we skip to this section? No. Where's our output now? I'm sorry. Hold on for a second. We have the variable on age. Oh yeah, here we are. Yeah, of course we skipped it. Yes. Okay. I was wondering where we were. So this is what we reviewed before. We reviewed the Iowa census data and the accompanying R code. We rounded it to 2 decimal places. I could revisit that. Now, one issue that some of you may have encountered, we have a question. So we have a question about 17. How many observational units are in the population? And the question asks, the rows of the data observations were greater. Well, in a census, because we're sampling everyone in the population, we're going to have a very large n. There it is right here, right? We can do the analysis to find this out, but here we have 55,000 3 people here. Now, if you want to look at the variables, I think there were 5 here. I think we even described that here. Yeah. Maybe not, I'm not sure. Yeah. But you can do that using the view function. I'm happy to open that though. I do want to get to these z-scores though, so we'll get to that. I'm going to open the code, in fact, that's relevant to answer some of these questions. Hold on for a second, if you don't mind. I just want to turn down the thermostat. It's a little hot in here. Okay. We're going to go to the code and hold on. We're going to open this with RStudio. So here we have RStudio with our code, and we're going to open the Iowa census data. So we'll file open. And I'll look for that here. Nope. Hold on for a second. I should have opened it. Let's see what happens. Huh. Okay. You know what I'll do? What was it? I tried opening the file separately. It didn't even work. I'm gonna file open. Oh. Sorry, it's just really hot in here for some reason. So we're opening the Iowa census data that we had before, and something seems to be blinking. It should be. Why can't I? Let's try to get them. Something seems to be going on. Sorry. Hold on for a second. Let me close another window. I'm sorry for the delay here. I'm not sure what's going on. Okay. There we go. Okay, good. I'm going to load our library. So we're going to run the script. Let me move these bars here. Those should not be here. So what you should see is you should see the R code. We're just going to load this thing up, and we're going to basically, I think I addressed most of these questions, but I just want to show basically, again, oh, that's strange. I'm sorry. File, open. Open, no, file. Iowa census data, open. Yes. Okay, there we are. So we have 5 variables here. We can see that here. Keep in mind, you can also use the view function. Nice, we do v. Oops. Make sure you click in. Make sure you click in the console, and then you do Iowa census. Keep the minus case sensitive, and then you can see those are the variables. Okay, so observational units. Observational units refer to the number of observations. These are the rows in their data frame. How many variables? Those are the columns. It's convention. It also may be context, though. I think some of you who have dealt with more complex data sets may have had other issues. Okay, what's the average years of education in the population? Well, here, this is where we're basically providing you with some of the code. Here, you're just taking the mean here, standard deviation. That's quite simple here. Right. Around 4, around 7, right? Around 7 and around 4. So that's about the population mu is around 7 for education. And we can sort of look at the context. What does education mean here? Could be years in education. That's what it looks like to me, actually. It's because it goes up to 12, has 0. I'm not exactly certain. But in 1915, having no education. Education probably wasn't as common, especially in rural communities, especially if you worked on the farm. But this is where context matters, right? You really want to check this out if you want to take this to publication. We're going to take a random sample of 10 people from the population and calculate the average years of education. We'll take another one without replacements. Again, I would say, I think this is misworded. I would say with replacement, because you basically want to have independent samples. You're just taking 2 samples. You're basically saying, okay, I'm going to take 10. I wish I had the bowl of beans that my roommate has. You just take 10 bean counters, actually, take 10 beans, estimate the X bar, that's the average. Take another 10 beans, assume that's average, take the X bar. And then we're gonna find that they differ. And your answers that differ are gonna be different than mine. And you can do this by defining objects here. So we can just basically define one object here. Remember, this is the assignment operator. And use a sample function. We say sample Iowa census, and the sample size will be of 10. And then you can print it, and you can estimate the mean of that. So there you go, 6.5. But let me show you this. You take a random sample of 10. It's just going to vary. We can do this forever. And this is why statistics had its origins in gambling, because this is almost like playing the slots. You see some variability here. You may, if you want to bet somebody, let's bet that we get a number above 8. I really lost that one, right? That's sampling variability. Well, now we're going to take 500 samples, and we don't want to keep pressing that. We use this little do function. It's pretty neat, actually. Do simply means we're going to basically take the mean of this variable education using the data, which is based on a sample size of 10. And we're going to call that Iowa 500. It's not the Indy 500, it's the Iowa 500. And there we have it. And we just did that once. And now we can do a histogram. Let's just take a look at the mean and standard deviation of this. This is going to be the mean of 500 samples of 10, and then this will be the standard deviation of 500 samples. Whoops. I'm going to clear out the junk here. So the mean is 7, and the standard deviation of these 500 samples is 1.21. Now, just if you want to know a little bit more about do, sorry, that's a 0. It's a rookie error. Remember, put the question mark before the function. You can basically figure this out, but basically it means to do things repeatedly. We're basically retaking the sample, retaking the sample, retaking the sample. I believe that's without replacements. If I'm wrong, shame on me. Yeah, I think it is, because it provides a natural syntax for repetition attuned to assist with replication and resampling methods. Typically, if we're doing resampling methods, we're going to do it without replacement. There's this whole technique called bootstrapping a standard error, which is kind of neat. Basically, if you want to increase precision, you take your sample and then you just take subsamples, and average those. I'm not sure why they call it bootstrapping. There's an idiom where you pull yourself up by your bootstraps, but it's a way to increase precision. But the main point is, basically, we take 500 of these 10 samples, and we have a little histogram here. And this is our sampling distribution, and this is pretty normal. It has a mean of around 7 right here on average. Our standard, we could say our standard error is going to be 1.25. So what would that be? That would be about 7th grade, I guess. Or if it went from 0, if 0 meant nothing, and 5 and 1 meant kindergarten, then you might have schooling up to age 11 or 12. on average. But you see some people having 10 years of schooling, few beyond that. Now, in the population, just keep in mind, we're going to take a look at the population again. Actually, we could do 5 more. I think we can do favstats. I want to use the favstats function. I'm just changing this up a little bit. You don't need to do that. If you look at this, you can actually see the max is 27. So the actual sample is larger. The variation in the sample is much larger than what we have here in our sampling distribution. But that's, of course, the point, because we're not actually interested in the full range of the entire population. We're interested in underestimating with some degree of precision what the average is. So what this histogram shows is the range of plausible values when we take 500 random samples, each with a sample size of 10. This is on average. This is an average of averages. Think of that. Is that right? Yeah, it's an average of averages and an average of standard deviations of samples. Right, it's sort of like a meta-analysis, really. Okay, and the point is, when we do statistics, we don't actually have to take 500 samples of 10. We can assume a bell curve, and we're going to infer a bell curve just by taking one sample of 10, and then we're going to make that assumption. And that assumption only works if we assume that we take a random sample. Here we take a, well, I want to go back to the actual question here. If we take 500 samples and calculate this, what is the shape of this distribution? It's a bell curve, mound-shaped, you could say. Mound-shaped, just think of a bell curve, approximately symmetrical and normal. When we say normal, think of bell curve. Normal does not mean typical. Normal is just the bell curve. So think of it as symmetrical. Simply means if we split this in half, right? If I just erased half of it, right? One side should be, look at a symmetrical face. One half should be the mirror image of the other. And it looks about the same. It's not skewed, in other words, right? Remember we talked about distributions being skewed. This is why we're interested in skewed. Okay, question 23. We're going to increase the sample size now. We're going to take, we're going to increase the sample size to 100. That's it. I did 1,000. The question here says 100. Maybe I think I changed that last time, just to show you what happens. So I know this is a bit of a repeat. So let's run this. Well, look at this. We have a much smaller standard deviation, and we should have the histogram there. Here we have it with the sample size of 100, sample size of 10, 100. So, and what really matters here is not necessarily the shape. Keep in mind the scale matters here. So here we have a range of 8 to 55, basically 12 to 3. So we have more variability, and when we have smaller sample sizes. So our point estimate, in other words, our estimate of the samples is about the same. It converges on about 7. The point is our precision changes considerably. Okay. I know I keep repeating this, but this is just crucial to emphasize. Compute this population mean and population standard deviation. Next, calculate the standard error of the sample mean based on a sample size of 100. That is, divide the population standard deviation by the square root of the sample size used to calculate the means. We did this before, right? We basically took sigma divided by the square root of n. Then, using the population mean and standard error of the sample mean, use the normal distribution to approximate the distribution of the sample means calculated previously. So we got a lot of questions here. Finally, use the standard normal to compare blah 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 with a sample size of 50. Well, good news is we have a lot of this code here for you. So let's run that. And as I showed to you before, what happens when you have a, how do they differ? Well, the distribution has with a larger n, has a smaller spread. And that's the blue one right here. And you can see that in the code here because we have the color red here, right? And we basically took the values from that one, and here's the sample size of 50. I guess the default would be blue. We didn't have to do the color as an option. So anyway, that's the point. So it's kind of what I told you before. I know I'm repeating myself, but this is important. It's inference. Okay. Now we're going to take this accompanying code to use this to talk about estimating the, what do you call it? The standard normal distribution. I think this is where we had some questions. To be clear, I also encountered a couple issues. I don't know if other people had with the pdist function. I think I fixed that, but I hope we don't run into a bug again. For some people on a Mac, it appears. Hold on for a second. For some people with a Mac, it appears that it doesn't seem to work. The pdist function, but it should not be a problem. Where's mine? I'm just going to go back to the homework assignment because I can't download from the PDF, I realized. Let's see if I can, actually. Maybe I can. Let's just check this out. No. Zoot. Okay. Oh, no, I'm sorry. Oh, sorry. I forgot that we had the code here. I believe. I want to make sure I had the right code. I might have changed it, though. I hope this works. If not, I deeply apologize. Okay, good. It does work. Okay. So here's the graph of the standard distribution with a mean 2 and a standard deviation of 1.5. I'm sorry, I made things a little too complicated. This is the problem of overthinking. This plot dist function, basically we define it as a norm, and I think this is where I ran into the typo before. Let's try this. So I didn't think that worked before. Is that, oh, hold on for a second. See, I thought this was the pdist. Yeah, it is the pdist function. I'm sorry. Okay. Now here's something that I ran into that was a bit of a problem. I'm sorry. Did anyone else, by the way, did anyone else run into this problem? I think this might be a version issue. Let's see this. Meh. Let's see, session info. I'm sorry. Sometimes if you have some issues, you might want to actually get a little bit of information, because this is where your version of R might actually affect what you get your code to work, whether or not you get your code to work. So let's run this. Ah, shoot. Okay. Well, I don't like this. Okay. 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 Did anyone else, Worked for me on Windows, exactly. Yeah, I know. Luis, do you have a Windows operating machine as well? Yeah, okay. So I think this has to do with something on a Mac operating system. And I can't say I can blame these people, but basically I'm going to describe to you basically conceptually what we're doing here, and what it should look like. And then I'll answer the questions here. And the logic should still work. When we create a plot of a standard normal distribution model, we want to create a plot with a mean 2 and a standard deviation of 1.5. We did that before. And that's what the plot dist function does. Right? And the standard distribution is a normal with a mean 0, standard deviation of 1. Right? And we basically define mean 0, standard deviation 1 there. And now we have something called a z-score, which is 1.5. You know that the distribution of age is very closely approximated by a normal distribution. What is Daryl's percentile to other people in the population? Round your answer to 2 decimal places. So what you do with figuring this out is basically you use the logic of a z-score. Well, actually, I'm not even sure if you really have to even figure that out, because you can basically say, okay, we know that the average is 0, and if we're 1.5 above 0, then we know that the standard deviation model is expressed as this. And you want to find the probabilities, right? So basically there are 3 things you can do with z-scores. And keep in mind, a z-score, all a z-score does is in essence, and I'll show you. A z-score basically tells you, a positive z-score of 1 would tell you that you're 1 standard deviation above the mean. A positive z-score of 1.5 tells you you're 1.5 standard deviations above the mean, or sigma squared or whatever. And because this is a probability distribution, all you should do, or rather, the main concept you should understand is that a z-score simply draws a line of a value. You know, this could be, Daryl, for instance, or this will be Nate's score, right? Okay, that's my z-score. It goes here, and with that value, you can basically estimate the area under the curve to basically to the left of this, right? So all of these, these little dots. If I could, I don't know, if I could draw with a little bit thicker line here, which is okay, that doesn't matter. But basically, if I want to fill in this space here, basically everything to the left of the curve, I'll spotlight it. I'll actually scribble, sorry. Right, everything to the left of this curve, all this stuff here, we estimate the area of this curve. And we know this by definition of what a z-score is. And this is probably where some of you said, well, okay. So for some people it works, for some people it doesn't. I'm not exactly sure. If it's the case that see, for me it worked earlier, I'm not sure. This is actually, to be honest, the reason why in the programming wars, there was a New York Times article about how popular R was, and the creator of SAS, which is another SAS program, said, well, if you're designing airplane wings, you probably don't want to use open source software. Sometimes some of these bugs happen. I thought I had this fixed, and not sure why it happens now. But basically all we're doing is we're just creating the normal distribution, and we're adding to it just a line, a demarcation point that is 1.5 above the origin, or the 0 value. So do we know that is Daryl older or younger than most people? He's older than most people because he's right around here. there's a greater area to the left of the curve than to the right. Now we have Molly's age converted to a z-score is -1. Is she older or younger than most people? Well, all we're doing here is we're creating the distribution with a q equal to -1. And it probably won't work either because it's the same argument. But the point is, again, it seems like it, so sometimes it'll ask for a default. Often there are default commands here. I won't waste your time figuring that out, but I will update with the message board. And if you miss that question, which you shouldn't have, because you could still answer the question by just simply understanding the idea of a z-score, right? A z-score of -1 means you're lower than everybody else, right? Just a relative value. So the point is, even though an SAT score or an ACT score, they're different scales, you can convert them to z-scores. And then you can compare different values. So here we have, for instance, Keisha. She was actually a high school friend of mine. I don't know if we meant to do this, but we know that she has 20 years of education, right? So we know that the average educational attainment is 10 and the population standard deviation is 5. So in other words, we're basically showing you how you can find basically take the population value. Hold on for a second. We can take the average is 10, and we know the population standard deviation is 5, and the distribution is normally distributed. Then we can find out her z-score, and that's simply what we do here. It's a simple arithmetic. So if we run this, it's 2, and that means that she's going to lie right here. She's going to be better than most right here. What are we doing here? Well, we're just taking the average for that person. This would be Keisha minus the population value, scaling it, dividing it by the standard deviation of the population, which means basically when we take our value for SAT, subtracted by the average and divided by the variation, we're making a ratio that is comparable across different types of scale measures. So for instance, SAT uses a different scale, 1800, you know, with a sigma of 300, whereas the ACT, I think, is like in the double digits, right? I think the highest is like 32. And the point is you can compare the relative percentiles and the relative distance by the z-scores. And a z-score, just think of that as a filler, because as I said before, a z-score, or if you're from the UK or the British colonies, you would say a z-score. It's a measure, a standardized measure of the distance in standard deviations, assuming a normal distribution. And if you do this here, you should be able to run this code here. Okay, so the problem here is we're not able to show that. So you can find the probabilities using a probability table. So this is where you would actually use the code here. So a z-score here gives us that probability. Now, if you notice, the probability of and below the critical points is always going to equal 1. That's because it's the sample space. Now, this is going to, okay, so this is, I can see why this is a little tricky for some of you, because if you have had issues with finding the z-score, you would have to probably look it up. I want to see if we even give you the percentiles for, I'm looking for a table that actually includes 1.5. Okay. If you have problem, I'm gonna tell the instructor If you have problems with a p-dist measure, then that is entirely our fault, because the p-dist function should give you it should give you the probability distribution. And I think that is just an error from the code that might require some default that is updated with recent code. So that is actually, okay. That is something, okay. What you should get with a p-dist function is you should actually get probability values from this. And I'm going to show you what you should get. For those of you who have gotten it, you should have no problem. But I know at least one student had that issue, and I did too. And I thought I fixed it, but let me show you this. Well, it's not showing the value. It's not showing what the output should look like. But the point is, you should be able to calculate the values. If not, another way is to actually just look at normal distribution probabilities z-scores. You could just Google this, and it's actually, I believe it's also in the textbook. Open intro stats. You almost look at every intro stats book, you're going to actually see the probability distribution. And I'll show you what this looks like. This would be on page 429. This is back before we had computers. We would have had to have actually estimate from the probability table what the distribution is. So for example, what the probability is. So for example, if we know a z-score is 1.5, we look at the table and look at what the z-score is, a positive z-score. We would see that the probability is 93.32. And the way I do that is I just look right up here. The reason is it's all standardized. It's just a very algorithmic function. Now, you can also sort of guess, basically, intuitively, that it would never be a 1.5 and a 6.6. These are just patently wrong answers, if you think about it, because this is 1.5 standard deviations above the mean. So it's never going to be that low. Okay, or no, would it be 15? Is he older or younger than most people? He's older than most people. Then we have a -1 score. Now, if you want to look at the probability of a negative p-value, a negative z-score, this would be on page 428. And here you have a -1. If you look right here, -1, it's simply the inverse, right? You're looking at just the area, this tail right here. What's the probability of this area here? And again, it's algorithmic. You just look at the table, and you would see it's right around, I'm going to say 15%, I think. Oh, we don't say, we say she's younger. Oh, we don't even ask for the exact probability? No, we don't. Okay, so we don't ask for the exact probability for that one. This you should have known. So there's only one answer for 25. No, I'm sorry. For 26, answer 26, that might be an issue. Same with answer 32. So there are two answers here that we might want to give you if your code didn't work, because that code should have worked for you. And it did work for me, but I don't know what happened. Okay, so but you can look at pages 428 and 429. So what you do is, what is the probability that a randomly selected person is older than Amy and younger than Maya, approximately? Okay, well, this is where it gets a little bit interesting, right? Now that we have Amy and Maya, what were the probabilities for Amy and Maya? Well, we have Amy. Right here. And then, so we want to find out the z-scores, right? That's pretty simple. And then what we want to do is we want to find out the probability for 1.5 and the probability for 0. Well, what is the probability? What's the z-score for 0? It's 50%. We don't even have to think there. What is the probability for 1.5? Well, we actually kind of already know what 1.5 is, don't we? We know it because we already answered that question for earlier. And because a z-score of 1.5 will always have the same probability. It's 93.32. So what we do is we take the probability of 93.32 and subtract 50%, and that's what is left is 43. So that basically shows us kind of the three things that we can do with z-scores. And yeah. And yeah, I guess it's fair with that even when the code doesn't work, feel free to let me know if you feel unjustly punished by the code not working. That being said, you should be able to find the probabilities with the table given the assigned text. But the point is, we can basically compare values. We can find probabilities, right? So your percentile, how much better did you do than others, or how many people did better than you? And by comparing values, I mean, we can actually say what percentage greater did one value than the other. We answered all those questions. I don't want to finish. I don't want to run out. So we have Keisha here. Remember, Keisha was, I believe, 2. So we can look at the probability 2. Well, that's 98% right here. And again, you can just look at the probability table. That would be page 429. In fact, and that's Appendix B, by the way. But you can also look this up. So 2 standard deviations is technically 0.9772, which rounds to 0.98. So she's better than 98%. Okay. Oh, I'm sorry. We skipped one. It's because we switched from different code. Okay. So for question 33, we ask, suppose from census data, you know the distribution of age in the population is normally distributed. Okay, this is important. You don't know Gabriella's age or z-score, but you know that the probability that a person her age is younger is 90. What is Gabriella's z-score approximately? Well, this is where you go from the table, and you can take, because we can take a z-score and get an exact probability, we can also take a probability and get a z-score. So here we take the probability table. I'm gonna just even, I'm just gonna show you normal probability z-score table. You can, I don't have to show you the text. I mean, I think it's not actually good, but I'm just downloading a PDF that is ubiquitous. Let's see if this includes positive. Yeah, this is basically, look at every stats book. Everyone has them. Okay, so we had, for instance, I wanted to show you. So if you have they're called standard normal probabilities. Standard means you can compare across different values. Here's the z-score. And here's the z-score, and there's the probability. So if we have a positive z-score of 2, it means it's 2 standard deviations above 0, which is 90.98, which was Keisha's percentile. She scored higher than that. Now we're asking, okay, given the probability her age is, so a person her age is or younger is 90, it means that she is 90% of the people in the sample are younger than her, there we have a value of about 1.3. You can round your answer to two decimal places. Well, how do you do that? Well, this is where you can look up here. We don't have that in the book, actually, but it's a little bit easier to look up. But you can say 1, you have a probability of, hold on, 0.90. You look it up here, sorry. You could be right here. I see this 0.89997, 1.28, right? So you're basically finding the probability and doing that here. You can also just basically, I'm pretty certain if you just Google, something, you can basically automate the z-scores. Because think how routine this is. You're basically saying, okay, I want one value, what's it translating to the other? Suppose you have for 34, we ask the average age in the population, and the standard deviation is 10. So on average, you're age 35, your sigma is 10. Using the information from question 33, right, we have basically, we know that Gabriella's z-score is 1.8. What is Gabriella's age approximately? Well, how do we know that she's 43.2 years old? Well, that's because we can basically, because we know what the z-score is, we can use basic algebra. So this is, again, how I'd answer this question. We know mu, we know sigma, and we know the z-score. Well, what do you do then? Well, we go and look at the equation for estimating a z-score. So we know mu, we know sigma, and we know the z-score. So what we do then is we would multiply our z-score 1.3 times sigma, and then add 35, which is, I think, right. Let's see, 1.3, about 11, plus 35, 46, 47. Yeah, that's about it. That's just a simple, that's the only thing we're doing is we're just asking you to kind of recognize that you can extract different kinds of information from the basic equation for the z-score. And that should be here too. Right, so here we have the z-score. I hope this works. This distribution should work too. No, it doesn't. Well, that's okay, because this definitely would work. No, okay. Well, in any case, I showed you how to solve these answers without using the code. And in the lecture slides, we showed you how to do it with the table. And technically, you don't even need the code. The code is the easy way out. But nevertheless, I do recognize we have some questions here that might require you to use the code. And if you have any issues, just let me know. But that being said, you should be familiar with Appendix B and the distribution tables, because it's really law-like. Very few aspects of statistics are basically numbers in, numbers out. And in this case, all the code is doing for the pdist functions is automating what is already readily available in the table and what we cover on in the lecture slides, or what you can even find online. That being said, I understand you might have some concerns, but I would say, like, for example, if you look at page 90, we say finding probabilities with a table. That should be something you should be able to do, especially keep in mind that this is going to be something that you're going to have for the final exam. So you could do it with R, but you should also learn how to find probabilities with a table. Because we're not testing you in code, we're testing you in understanding and analyzing z-scores. So the main point is z-scores are flexible, and they are a way of standardizing values and comparing values that have different scales. And that's really the second component of this week. I think we had quite a bit here. But just keep in mind, the first part has to do with probability distributions. The second part has to do with understanding that this is similar to our week on probability. Remember, our probability, our sample space is always 1. Well, here we're representing our sample space as a average of samples. And those average of samples approximate the Bell distribution. And we can safely assume that our margins of error, our confidence intervals, whenever we take a random sample, is going to approximate the Bell curve. And this is the greatest insight that statistics has. This is their bragging point, and it's something that you'll keep with you as you continue your statistical career. Okay, I'm going to stop recording right now, but if you have any questions,